So I wanted to do a quick video on this nonsense. So if we're looking at something that has this structure, right, and everything is different, or at least there's a difference, but if you cut this in half and there's a difference between these two sides, all right, you can make, because you have two chiral carbons, and again, what is a chiral carbon or a stereocarbon or stereocenter is that this is attached to four different things, all right? So to do the first isomer, stereoisomer, you just pretend that this is looking into a mirror, and you just draw it like it's looking into a mirror, okay? These are called enantiomers. Then what I do is I look at these two things as like arms that can kind of like rotate. So you're only going to move one thing at a time. So you're going to do this one, and this carbon is going to kind of pivot around, and the white is going to come here, and the green is going to come here, and that's going to create this form, okay? These are not enantiomers because they are not mirror images. Blue is on top of white. You'll never have that make a mirror image, okay? They're what's called diastereomers. Anything that is not a mirror image is a diastereoisomer. I don't know if I'm saying that right. What we're going to say is B and D, diastereo. There's a difference there. A and C, diastereo. Okay. The other change you want to do, we switched white and green. We're going to look back at our original, and we're going to put white and green back where they were. But this time, we're going to switch green and blue, just like this. And we're going to create our fourth stereoisomer. The other thing you could have done, if you remember that this is a mirror, is just draw the mirror image of this one, right? White matches to white, blue matches to blue, red to red, purple to purple, green, green, okay? These are enantiomers. They're all chiral and optically active. They're chiral because they don't have a plane of symmetry. That would cut this in half and everything would be the same, okay? And these are all isomers because they all have the same chemical formula. Something else that can happen is if we look at a molecule or a compound like this, okay, we still have two chiral centers. So you would think that you would also have four isomers. This isn't the case, and I'm going to tell you why. We still have a mirror coming down here. So these two are mirror images of each other. But when you think about it, we drew the same thing. Right? You can cut this down the middle, and you have the same thing on both sides. Well, I actually, not necessarily in this case, I think what I was supposed to do is technically make this red also. But I think this still stands because you could cut it down the middle this way also. And they're essentially the same thing, which means that these are what's called meso.
That's again diastereomer. Anything that is not a mirror image.
Okay, so this one is really only going to have three. This is a good question, whether this has to be red or not. I'm going to ask him that. But we can do the same strategy that we did before, and we can pivot our green for our white. We can return that to where it was, or we can draw the mirror image here. So these are mirror images, which means they are chiral. They're diastereoisomers, or diastereomers. Okay, but remember, B and A is the same. So for this one, technically, there's only 3 stereoisomers.